So everyone, my name is Einig. I'm a PhD student here in IRAM Grenoble, supervised by Jérôme and Jocelyn Chanusso. And you will have me for 30 minutes to talk about two different works in the context of the Orion B consortium. Let's begin with the denoising of the Orion B observations. So just a few words about the data that's already been presented by Jérôme. We have almost 30 molecular line cubes for the first transition that are spatially and spectrally resolved. There are about 1 million pixels and more than 200 velocity channels. And this is a kind of part of the 13 CO cubes. And so just a few of the integral and the mean profiles of the data. And what we can see here is that in function of the line that we are considering, the signal-to-noise ratio can vary a lot. And it's important because for some statistical analysis, this difference in the signal-to-noise ratio will have an impact on the relationship that we can detect between physical parameters and line intensities. So this is a main issue, and this work has the goal to find a solution in order to extract more signal from noisy data. So the denoising considered that you have true signals in the observations and that you will be able to find a function f such as you are able to extract the signal from the data. So generally, the most simple case is the case of additive noise. So you have the data that are equal to the true signal plus an additive noise. And in the case of hyperspectral cubes denoising, there are plenty of algorithms that have been developed since decades in the remote sensing community. But those methods are essentially developed with Earth images, and they will be that they are quite different from the astrophysical hyperspectral observations. And the question is, what about the molecular line cubes that we have in the Orion B dataset? One of the methods that is the most performant in order to denoise the hyperspectral observation is the denoising by dimension reductions. So they make the assumption that the extrinsic dimension of the data is much higher than the intrinsic dimension. The extrinsic dimension will be, in our case, the number of velocity channels, and the intrinsic dimension will be a dimension of reduced data in a lower space. If this is the case, we say that there is a lot of redundancy, and this redundancy can be exploited in order to extract signal to correct the measurement. But to be able to do this, we have 2 points that we have to match. The first one is that the intrinsic dimension of the measurement has to be really lower than the extrinsic one, and this is not mandatory. And the second one is that we have to know the relations between the original signal and this compressed signal. This denoising by dimension reductions can be difficult to understand, but in fact, there is something which is very close to it that exists in the astrophysical community. This is the Gaussian fitting. For instance, if you have a profile like this with a Gaussian shape plus noise, you can encode this profile with a lot of values in only 3 values. For instance, the peak intensity, centroid velocity, and the dispersion. And then at the end, you will be able to reconstruct after the decoding a signal. And then this can be seen as denoising by dimension reduction because you reduced 100 values into only 3 values you reconstruct, and you have a signal without noise. In our case, it can be, and the algorithm that you used in order to do this encoding and decoding try to minimize the distance between the original data and the reconstructed data. In the case of the machine learning community, this is called the loss functions. In our case, we'll use another method, which is based on the autoencoder neural networks. In our case, we won't make the hypothesis, the assumption of Gaussianity of the data, which is quite a strong assumption. And we'll just train neural networks in order to learn by itself the encoding and the decoding of the data. And we hope that after the encoding of the data and the reconstruction, there is a part of the signal of the observation that will be filtered out. And we hope that this part of the signal, which has been filtered out, it's the noise. So we'll give to the networks the profiles, so pixels of the data. These pixels will be processed one by one, reconstruct, and iteration after iteration, we hope that the networks will be able to denoise the data properly. So which means that at the beginning, you give profiles and the denoising is not good, but after a lot of iteration, you can converge to a solution where the noise has been filtered out. What I think which is important is that the same encoding and decoding functions are used for every profiles of the cubes. But what's important is that if we try to denoise different cubes, we have to train different networks. So in the case of our cubes, the noise is a little bit difficult to model because this is it depends of the dynamic of the noise depends of the pixels and also to a lesser extent to the velocity channels. And one of the things is that this method by dimension reduction works very well with the Earth observations aperture cubes. Which looks like this. So they are continuum cubes, and they are quite different for the line cubes. We are composed of pixels, basically. And one other difference can be seen in this kind of figures. So this is something which is called correlation matrix. So we compute the Pearson correlations between two different channels of the image. And this is what is obtained for line cubes, and this is what is obtained with a continuum cube such as the one that are used in the hyperstructural community. And they are quite different. And here we can see that the redundancy, the correlation is high for the channels that are close to each other. And this is not the case for standard hyperstructural data, where you can have a lot of redundancy between channels that are really far away from each other. And this is something which will be a problem in our case, because we have a very low information redundancy and only a local redundancy. So to start with the autoencoder I've shown before, the first proposition in order to adapt the method to a specific case of astrophysical cubes will change the loss function in order to add more information, and this information, this additional information will be to indicate to the model if we think that a voxel is composed of a signal plus noise or only noise. The neural network will be able to use this prior, maybe adapt it if we think that we are wrong, but it will help it in order to have a better result at the end. So the loss function is not anymore just a mean squared error, but something which is a little bit more complicated. But at the end, this is same kind of things. This prior is obtained from a three-dimensional segmentation methods, which has been developed, in fact, by Jerome. But I won't give a lot of details on it, but with something which will segment the cubes in 3 dimensions, and for each voxel will indicate 0 and 1 if whether we think that the voxel is composed of signal or not. So as I said before, there is one problem, which is that distant channels share almost no information. The redundancy was close to the diagonal, which means that the redundancy were present only for between channels that are close to each other. And so a solution for that will be to adapt the architecture, the standard architecture of an autoencoder to something like this, where we are able to encode the velocity channels only if they are close to each other. And this is something which will prevent the encoding of channels that share almost no information, that will reduce the number of, importantly, the number of weights in the networks by something which is close to 90%, which is very important. And so a network with less parameters will be easier to train, and we obtain results that are more interpretable. To compare our results, we'll compare our result with the Rosa-Gaussian fitting method, which is used in order to extract the multi-phase structure of the interstellar medium. This is a spatially constrained Gaussian decomposition of the signal, and the decomposition and reconstruction can be seen as denoising, and so we'll compare our method with it. I there are other frameworks that works a little bit like ROSA, such as GoSpy Plus, but we'll compare results specifically here with ROSA. So the first one is the RMS of the residuals integrated on the spectral axis for the autoencoder on the first row and ROSA on the second row. And we can see that the result when we divide by the dynamic of the noise is really different between the autoencoder and ROSA. In the case of ROSA, we have a lot of signal that appears in the residual, which means that the signal has been distorted during the denoising, which is not very good. In the case of the autoencoder, this is a little bit different. So you have some part of the signal here, which corresponds sometimes to outflows or something close to the dense cores, but really less than for ROSA. But the dynamic of the image is close to something which is blue, which is a little bit lower one, which means that in some region, the autoencoder has choose to not denoise the data because it's considered that the signal to noise ratio was already good, and to try to denoise the signal will lead to a distortion of the signal. So it's preferable here to not doing anything. And this is why the image is mostly something which is blue, so under 1. A visual example of the denoising is this one. So the autoencoder is on the top panel and ROSA on the bottom panel. And we'll have something like this. So this is the raw image. This is the denoise image for the autoencoder and for ROSA, and the residuals, so the subtraction of the inputs and the outputs. In the case of the autoencoder, we cannot see a lot of signal in the residual, which is good. In this region where you have more signals, the residual are closer to 1 because the autoencoder is very careful when he is denoising. The denoising is performed well on the diffuse region. In the case of ROSA, you can see that the dense core appears in the residuals. So as a conclusion, the usual dimension reduction methods are poorly adapted in the case of molecular line cubes because they are quite different from the data that are usually studied in the hyperstructural community. So in our case, we have developed a deep learning method which is based on an IPDET data analysis. And we are able now to denoise the cubes with behavior which depends to the signal to noise ratio of the data in order to avoid distorting the signal. And this result has been published in AAA last year. And there is a GitHub that contains the code to reproduce the result and to have access to the figure, which is completely available on GitHub. So you can try it, and it can be used for other data sets. For any line cubes that you will change the architecture comparing to the one that you have used in the case of the Orion cube, but it's completely available for any line cubes that you want. Thank you.
Very interesting questions. Yeah, short one about the comparison with ROSA. So
this one, maybe?
Yeah, or the next one. But ROSA, if I remember correctly, has a fixed number of quotient components of the entire field.
Okay.
So I guess part of the failings of ROSA, maybe due to the fact that the profiles are not perfectly Gaussian. And if you want to follow the field exactly, you use a lot of your Gaussians to fit one component, and then there's a bit of signal that you have to leave. So how does changing the number of components hard-coded in ROSA impact the comparison with the encoded?
In kinematics, the difference is, as you said, sometimes the peaks are not completely Gaussians. In this case, I think the restriction was to only 5 Gaussian by profile. So sometimes the difference can be this one, but this is one of the difficulty with ROSA. We have these hyperparameters of the number of Gaussians, which is important, and this is difficult to really find a good value for these parameters. But yeah, in this case, this is one of the reason why the result of ROSA in some velocity channels are quite different from the one that we have with the autoencoder. This is the problem of ROSA, is to find a good value for these hyperparameters. There are other methods where we don't have to fix global values, but the value which is dependent for every pixels that can be useful. Is the case for GoSpy Plus. I don't know if it's answered.
The referee asked for a comparison with GoSpy Plus to see whether this was we would see difference due to the fact that we are not fixing the number of Gaussian components, and the problems that we see here are similar to the ones we have with GoPy+. So it's not a problem of number of components.
Sometimes it can be, but here it is integrated on every velocity channels. So it's more than the profiles are in some regions are not Gaussian at all. And so this is the reason of it.
Well, as you know, I'm very much impressed by the work you're doing, and this kind of denoising algorithms are very interesting. I have a question because you were saying before, distant channels share almost no information.
Yeah.
And I would disagree with this in the sense that the 30-meter telescope has narrow beam. So you're catching information from somewhere else and you're putting it into your primary beam. And this information is not necessarily at the same velocity. So the question is how you're taking care of this, or if you are simply omitting this and considering this is also noise, whatever, I mean, the signal, whatever, from wherever the signal is coming from.
I'm not sure I completely understand. In fact, there are information, for instance, this figure where there are distant channels that share a bit of information. But in the case of when you say that there is information between distant channels, I think that this information is so faint that it's not really usable in our case. So in the case of the architecture that I present, this information is just ignored. So that will be my answer. Maybe we should be able to use it, but the question is that, is it worth trying to extract this information? I'm not sure.
Maybe this is more important at higher frequencies, not where the secondary beam is so huge, but you can collect the signal from other regions of the cloud, no?
Maybe.
But in the 3 millimeter, maybe it's more narrow beam. So I have a question, how much time do you need to denoise the Orion B cube? And is it possible to code in cube so that the users can use it?
That's a good question. It's about 1 hour and a half for a cube, but you have to train a new model for each cube. So, and is it possible to implement it in GILDAS? This method used the PyTorch library. So for now, I don't think that's possible. Absolutely, it's possible, but now I don't think it's worth the try.
No, we
I don't
decided,
think
so we decided that Luca would put his code in GitHub with PyTorch because there is no point to try to record the PyTorch in GILDAS. The method that use because there is a prerequisite that is to give a prior about where the signal is in order to train the stuff
Is it GILDAS?
is done in Cube. It's coded in Cube.
Very interesting.